So this is probably where we started last year when we were talking about the periodic table. You had a situation where historically they were discovering new elements. There were some that they had known about for a long time, and they were discovering new elements, and they were trying to see if there was some sort of pattern to the elements. In other words, if they could put them into categories. They suspected that that was true because some of the elements had similar properties, like the alkali metals they knew had similar properties. So they were looking for a way to express that idea of a regular pattern. So again, this is something that we talked about before. So when we are using the sort of more standard representation for the electrons, the electron configuration, then we have a certain pattern or a certain sequence or sequence of filling that we follow. So we fill the lower levels first, and we go in the order that we discussed previously. So there's a rule called Hund's rule, and the Hund's rule is the name for what we said last year, that within a particular sublevel that the electrons will spread out into different orbitals before they pair up. So that's referred to as Hund's rule. So here we have the electron configuration for oxygen, and then we also have this representation. You can use circles or squares, but you use arrows up and arrows down. So this represents the 1s1 and 1s2 electrons that are in this s orbital. Same thing here for the 2s orbital. And then here we see that the electrons spread out. Well, maybe we don't actually see that completely, but, well, I guess we do. So this one over here in this last little box wouldn't pair up, right, because you have to use all the orbitals first before you can start to pair them up. I think it makes sense that when atoms bond to one another, that it's going to be the outer electrons that are the ones that are typically going to be involved in forming bonds. So we refer to those electrons, those outer electrons, as valence electrons. So they are the electrons that are in the same group, and they are the outer electrons. So it is important to recognize that the periodic table is in fact arranged by electron configurations. And what I mean by that is that the configuration for all of the atoms in a particular column, like this column, all are going to end in S1, and all of these are going to be S2s, and then we're going to have the D's from here, so this would be D1 over to D10. And then we pick back over here, so this is going to be the first of the P electrons, so P1, P2, P3, P4, P5, P6. And then we have the F's, which are really the filling of the, represent the filling of the F sublevel. So if we just want to know quickly, so for example, what is the configuration for, I don't know, this particular atom here. So without knowing anything more, we can say, well, it ends in 5s2. And that's really the important thing. I mean, we could write out all the electrons that lead up to that, but that's not really the important point. The important point is, what are these valence electrons? All right, so the question here is to find the expected or the predicted electron configurations for each of the following elements. So let me pull up the periodic table, and I guess I did this out of order, but here's barium. So we see barium down here. There's barium. So barium is going to be the same as xenon, which came before it, but then in addition, it's going to have a 6s2, okay? And the one before that we were asked about was sulfur, and sulfur is here. Let's see, I'll do it like this. So sulfur is over here, and we expect sulfur to be the same as neon, which is here, and then sulfur in addition is going to be 3s2, 3p4. And then finally we're asked about europium, which I think is actually cut off. So, well, you would just follow the same process, except that europium would end up with in an F sublevel.